everyone, welcome to the second part of our lesson on wave interactions. Now in the first part, in our last video lesson, we started talking a bit about what makes a wave and why we model certain things as waves rather than as particles or matter. The reason being that waves exhibit certain behaviors that particles and objects don't necessarily exhibit the same way. So we've already talked about a couple of these wave-unique behaviors. We've talked about reflection. We've talked about interference, that ability of waves to occupy the same space and either add or subtract from each other. And then from reflection and interference, we can get standing waves that seem to oscillate in place. And we talked a bit about resonance as well. And all of those are going to be really important as we consider how to design and construct our musical instruments. But there are a few other wave behaviors that I wanted to introduce you to a little bit, in part because they're just like fun and cool and weird, but also because some of these wave behaviors are going to set us up really well for our final unit on astronomy. It turns out some of these are useful as we're doing astronomical and cosmological research. So buckle up. It's going to be great. All right. Now, before we dive in, here's a little not especially physicsy question for you. Consider this image that is shown to you right now. What is this image trying to communicate? So I think you probably understand, hopefully, that the image is telling you that you shouldn't talk or yell or sing or otherwise, make noise with your mouth. And in order to pick up that message, you had to see these little lines coming out of the person's mouth as representing sound coming out of his mouth. And it turns out that in addition to, telling people to be quiet, that representation is also really useful in a scientific context as well. We call these little lines that are emanating out from a source wave fronts, okay? And so that's another way, in addition to the classic sine waves and things like that we've already used. Wave fronts are another way for us to model and diagram the movement of waves through space. Now, probably the simplest way for us to think about what those wave fronts really mean is if we're talking about a transverse wave, we can think of these fronts as representing the crests of those transverse waves as they move away from the source of that wave. Okay, so as we see the wave moving along and a single crest is moving along, that's represented by one of these wave fronts here. For longitudinal waves, on the other hand, they don't have crests and troughs. They have compressions where particles are really scrunched together and rarefactions where our particles are really far apart. And so we can think of these wave fronts for a longitudinal wave as representing compressions, places where there's really high pressure in that space due to the particles all being close together. Now, just so we can kind of see this a slightly different way. So we're jumping over to a PhET simulation because I love me my PhET simulations. And over here, we've got a speaker, right? And so I'm going to turn on the speaker and we can see that it is producing these sound waves and it's being represented as these wave fronts that are emanating out in this sort of circular kind of fashion there. But then just so you can kind of see how that relates to what the wave is actually doing, I'm going to go ahead and superimpose on this image a diagram, a model of what the particles are doing as a result of this. So this looks like crazy, right? But if you look at what's happening with the particles, you see that in the places where we have those, the white wave fronts coming out there, that's where our particles tend to be all bunched together. Those are the compressions of the sound wave as they move through those air particles. And then in the places where we don't have those white wave fronts there, the black spaces in between, those represent our rarefactions where we have fewer particles, all right? So just to kind of contextualize a little bit of what we mean when we're talking about these wave fronts. Okay, cool. So now that we have that that representation of waves in our toolkit here, let's talk about those three other wave behaviors. Okay, so one is called refraction, not the same as reflection, refraction. Okay, and refraction occurs when a wave bends as it goes from one environment to a different environment. Because as we mentioned before, the one thing that determines the speed of a wave is the medium. that it is in? What is the material that it is traveling through? And so if I have a wave that's moving along through air, for example, and then suddenly that wave strikes glass or water or plastic or whatever, the wave is going to move at a different speed through the glass, water, plastic, whatever, than it did through air. And as a result of that shift in speed, it will actually turn a little bit, that the side of the wave that hits that new medium sooner will move, in this case, more slowly than the part of the wave that hasn't hit that medium yet. And so the whole wave ends up kind of like turning towards the medium that, in this case, it's moving slower in. And so we've got a representation, an animation of it on the left here. Over on the right, you can see a photo of refraction in action. So we've got a light being directed at an angle at an acrylic block right there. And so you can see that as the light's moving in a straight line initially, and then once it hits the block, it's no longer continuing on in the same straight line. It curves downward. It bends downward and then continues on in a straight line through the acrylic from there. Bonus question time. What other wave behavior do you see in this picture? Look, there's a little bit of reflection right there. You can see the wave bouncing off the boundary there, bouncing off that interface, and going back up and to the right there as well. So in this picture, we get 2 for 1. We see both refraction and reflection. Cute. All right. So that's refraction. The next wave phenomenon is called diffraction. So there's reflection, refraction, and diffraction. I am sorry, I did not choose these names. Okay, so diffraction occurs when a wave encounters some sort of obstacle and basically bends around it, and as a result ends up spreading out. And so we can see 2 different representations of this, a still one on the left here, so that we can see how if we sort of draw these sort of radial lines through the different wave fronts, we can see how those lines are kind of spreading out and bending. And then on the right, we also have an animation. So we see these wave fronts that are moving along. They approach a wall with an aperture or an opening in it. And so the wave fronts go through that opening and then bend and spread out so that they're sort of like going around the walls almost. So that's a basic idea of what's going on with diffraction. Now, again, I did not choose these names, and I recognize that they can be a little bit confusing. So let's focus in on the difference between refraction and diffraction. Both of those involve waves bending, but what is different about those 2 behaviors? So ultimately, both involve waves bending, but for refraction, the reason that the wave is bending is because it is now entering some different medium. It's passing through a new object, whereas diffraction, the wave is going essentially around the object. It's bending around that boundary and spreading itself out. So for refraction, there is a change in the medium that the wave is traveling through. For diffraction, there is not a change in the medium. It's just going around the boundary. So that's the difference between those 2 phenomena. Okay, now I've got one more behavior that I want to mention to you. This one is fun, and it is called the Doppler effect. So let's watch and learn and enjoy. I stole this video, by the way, from BYU, so they explained it so beautifully, so I'm just gonna let them do it.
All waves travel outward from a source. A stone dropped in a pond, for instance, will produce waves that move out in a circular pattern from the splash. Light works the same way. When a camera flashes, light waves move out from the flash bulb. When the source of a wave is stationary, the waves can be thought to form circles radiating out from the source. But when the source is moving, something very interesting happens. The waves ahead of the moving source are bunched closer together. The waves trailing behind the moving source are spread out.
We hear this effect when a moving car blows its horn as it passes us. We hear a high-pitched sound as the car approaches us because the motion of the car bunches the sound waves closer together. When the car passes us, we hear a distinct drop in pitch because the sound waves are now spread out by the car.
The video should have explained for you the essence of the Doppler effect, which is an apparent shift in the frequency of the waves that an object is producing if it is moving relative to the person who is observing those waves. Okay, now I say apparent because there's not an actual shift in the frequency of the waves being produced. It just appears that way. Okay, so if we're continuing on with the example of the car horn as it's going there. Okay, so the car represents then the object, the source object that is producing this this sound. Now, if you're inside the car and you're hitting the horn, like, it sounds the same to you no matter where you are or how fast you're going, because you're not moving relative to the car, you're moving with the car, so there's no change there. But if you are an observer outside of the car, it sounds like a higher frequency when they're coming towards you because those waves are getting all bunched up, essentially. And as the car is moving away from you, the waves sound lower pitched because essentially those wave fronts are getting spread out. All right, so I just said exactly what I was going to put here with that. Okay, so as you get closer to the source, you're going to observe a higher frequency. As you move apart, you're going to observe a lower frequency. And the faster this relative motion is, the more pronounced we'll see that change in frequency. So just to kind of give us a chance to play with that a little bit, we've got another little simulation right here. With airplanes producing sound. All right. And so we'll start off with just like a regular, like it's just sitting there. It's a stationary plane. It is producing these sound waves. They're emanating out as wave fronts. No big change. That's not very exciting. But as we start to get the plane moving, we can start to see how the wave fronts are all bunching up in front of the plane and then getting more spread out behind the plane. And then as we get more and more quick here, we end up seeing more pronounced bunching up here up at the front. And then we can get a really fun thing where we break the sound barrier in this case. At which point the plane is able to move faster than the wave fronts can, right? So you're moving faster than the sound waves can move through, so all the waves are just bunching up and you're just kind of moving out ahead of them. This, by the way, is also how a sonic boom works, because basically, let's go nice and fast here. Woo! All right. So you get all these waves that are all bunching up together. And so there's nothing, 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 nothing. But then as soon as all of those bunched up wave fronts all hit you, there's a huge amount of constructive interference right there. And so you end up hearing a really, really loud sound. So cute. All right. So that is the Doppler effect. One last check for understanding. Say we've got a fire engine moving along to the left here, and it's got its siren going because they gotta save lives, dang it. So we've got 4 different people here in locations A, B, C, and D. Who is going to hear the highest pitched siren as the fire engine is driving? And there may be more than one correct answer. So. All right. So for this one, the person, or I should say the people who are going to hear the highest pitch are person A and person B. It doesn't matter how far away from the fire engine they are. The fact is that the fire engine is moving towards both of them at the same velocity. And so they'll both hear the same increased pitch as a result of that. Person C in the fire truck isn't going to hear any change at all. Person D will hear a lower pitch siren because the fire truck is moving away from them. All right, that's it. So that's all of our wave behaviors that we're going to be really focusing in on here. And so we'll do a little practice. We'll make some musical instruments. It's going to be great. All right, thanks, folks.